Hello. Ooh, bright lights. Thank you. Thank you all for coming. My name is Adam Beglin, and I'm a solutions architect on the high-performance computing team here at AWS. I'm really excited to talk to you guys today about a subject that I'm really passionate about, which is EC2 performance. See, I've been a system administrator most of my career, and I know how frustrating it is to not get the performance that you're expecting out of an EC2 instance or out of a server. So what I wanted to talk to you today is about some of the things that I've learned and that my customers do in order to get the best possible performance out of EC2. My customers are doing things like computational fluid dynamics and gene sequencing and semiconductor design. So as you can imagine, performance is a really important subject to them. So I'm glad that I can share this information with you guys today. Now, this presentation, it's definitely built to be a deep dive on EC2 performance. And we're going to dive pretty deep into the nitty-gritty of how EC2 works. But along the way, I also want to make sure that I'm highlighting actionable things that you guys can walk away with and actually apply to your instances in order to get them to run at their full potential. I'm also going to talk a little bit about things that go into choosing your EC2 instance. Because when it comes to getting performance out of an instance, making sure that you're picking the right one is just as important as all the performance tips that I'm going to give you during this presentation. Go over to this side, the thing works a little bit easier. Now, EC2, it's a really big subject. And when you talk about EC2, you can talk about a lot of different things. You can talk about the different ways of purchasing EC2, all the APIs and SDKs that make managing it easier. You even talk about the networking that backs every EC2 instance. But what I'm going to cover today are the EC2 instances themselves, how they operate, what their features are, and all the options that you have when you go to launch them. For all those other subjects, I'm going to be giving some recommendations for other presentations here at reInvent that'll dive deep into those. And I'll give those at the end of this presentation. So let's start at the basics. What is an EC2 instance? Well, EC2 instances, they are virtual machines. So they are guests that are sitting on top of a hypervisor that's running on a piece of physical hardware. And when we launched EC2 about 10 years ago in 2006, you didn't get a lot of choices. You didn't get a lot of flexibility. You went to launch and you got a instance. You didn't get to pick how many virtual CPUs it had or how much memory it had. It was kind of like the original Model T, where you could have any color you want as long as it's black. Or in our case, we made it orange. And we eventually gave it a name. We started calling it the M1 instance. But customers, they wanted more flexibility and they wanted more choices. So we started iterating on the platform. And as you can see, we've been growing really significantly ever since. But not only have we been adding more EC2 instances, we've actually been quietly changing how EC2 operates underneath the hood. A good example of this is in 2011, when we launched the CC2 instance. This was the first instance where we actually gave you the ability to define the physical topology of your EC2 instances, and that was with placement groups. So with placement groups, you can actually define that your instances be located physically close together to get you the best possible bandwidth and the lowest possible latency. This was also the time where we introduced hardware-assisted virtualization. And HVM is a great feature because it allows you to use more of the underlying hardware and not spend so much time talking to the hypervisor. Now, EC2, it's always growing and it's always changing. Even the things that I talk about today may be different in the future. So whenever you're designing your infrastructure, make sure that you're looking at our documentation to find the latest information available on EC2. Now, before we dive into the instances and dive into the tuning aspects, I want to be sure that we're starting with a common language. So here you can see the name of an instance. It's the C4 extra large. And the C in C4 is the instance family. Now, the family stands for what the instance is best suited for or what resources it has. So you've got C for compute, R for RAM, I for IOPS, so on and so forth. The next number you see is the instance generation. And you can think of this almost like a version number of your EC2 instance. So a C4 instance is newer than a C3 instance. And lastly, you have the instance size. And I've heard these called t-shirt sizes, which is a really great way of thinking about them. So you've got small, medium, large, extra large, so on and so forth. And what all this means for you is that you have a lot of choices and you have a lot of flexibility when you go to launch your instance. Now, I know when you're in the EC2 console, it can seem pretty overwhelming when you're faced with that giant list of instances you're trying to launch for your workload. So my suggestion to be able to pick the right instance is to first start with the instance family. And to find the right family, you need to look and understand what your application is constrained by. So if your application needs a lot of memory, start with a RAM-optimized instance like the R3 instance. If you need a lot of compute, start with the C4. If your application's actually pretty well balanced, you'll probably want to be in the general purpose category with an M4 or a T2 instance. By choosing your instance from the perspective of your constraint, it's pretty easy to find the right family, and then from there, it's just a little bit of testing to find the right size within that family. If you still need a little bit of help, the EC2 documentation actually has a list of workloads for every single family that are well suited for it. So it's a great option to go if you're not sure. But when you're going to launch an instance, you'll see something, a property of that instance that you've probably not seen outside of AWS. And that's the VCPU, or virtual CPU. And I have a lot of customers ask me, what is a virtual CPU? Well, a VCPU, or a virtual CPU, on modern instances, except for the T family, which is special for reasons we'll talk about later, it's actually just a hyper-threaded physical core. Now, hyper-threading is a really cool technology that lets you get more out of your CPU. So it lets your CPU do almost two things at once. So normally, if you have a process that would be blocked on I/O or waiting on a user, it would be stuck and your CPU wouldn't be able to do anything. With hyper-threading, that CPU can wait and process some requests as they're coming in. Now, we have some customers who want to know their real core count or their physical core count on their instances. And to do this, you can usually just divide that VCPU number by 2 to get that core count. We also list, for licensing purposes, a list of every EC2 instance and how many physical cores it has on the link that you see below. And to visualize what a virtual CPU looks like, here's the output of a program that I like to use. It's called LSTOPO. That's LSTOPO. And I really like it because it gives you a visual representation of the underlying physical hardware of your instance. So here you can see the output of an M4 10x large instance. You can see how many sockets it has, how much memory is assigned to each socket, the level 1 through level 3 cache that it has. But most importantly, for these purposes, you can actually see the physical core count and then the threads that are assigned to each core. So in the case of the M4 10x large, you can see that you have 40 threads and 20 physical cores. Now, there are some applications that actually don't benefit from hyperthreading, where the context switching involved in them can actually slow down the performance. These are typically compute-heavy applications, things like financial risk calculations and engineering simulations that spend a lot of time working on that processor. These applications, both on-premise and on AWS, usually disable hyperthreading. Now, if you're not sure if this applies to your workloads, look at what you do with your on-premise or your bare metal machines, or what your coworkers do. If you normally disable it on-premise, you'll probably also want to disable it on AWS. If you're not sure, you probably don't need to worry about any of this. But it's really easy to do on Linux, slightly harder on Windows. On Linux, the way threads are enumerated makes it really easy to turn off that hyperthreading. So let's say you have 2 processors. The A threads of each processor are listed first. So say 0 through 10 on a M4, and then you got 10 through 20 on the other CPU socket. The B threads are then listed second. So to disable hyperthreading, all you need to do is turn off those B threads. And you can do this 2 different ways. The first way that you'll see here is you can do it online. So this is just a simple for loop in Bash. And what it's doing is it's disabling every online processor. Now, this is a great option because it doesn't require a reboot. However, the downsides of this is that it could potentially cause system instability because you're disabling processors that applications might be running on. You'll also lose all these changes once you reboot the machine. So the way that I prefer is the second way, which is just in Linux to set a grub boot parameter for the number of physical cores of that box, -1 because it starts at 0. The only downside of this approach is that it does require a reboot, and that if you ever change from one instance size to another, you're going to have to remember to update that setting. On Windows, this process is a little bit harder, and that's because instead of listing the A first and then the B, like Linux does, Windows actually interleaves the A and the B processors. So in order to disable hyperthreading on a Windows box, you've actually got to use something like CPU thread affinity to lock specific processors to their specific physical cores. And here you can see that same output of that same M410X large, but just with hyperthreading enabled. You'll notice now that there's one thread for every physical core, whereas there were 2 earlier. So next, let's dig a little bit deeper into how instance sizes work. The way we build instances actually is built to allow you to scale pretty easily, both vertically and horizontally. So let's take the C4 family as an example. Here you can see on the left is the C4 8X large instance, which is the largest C4 instance that we have available. That C4 8X large instance is roughly equal in resources to 2 of the C4 4X large resources, C4 4X large instances, sorry. And these are things like virtual CPUs that instance has, the amount of memory that's allocated to it, even the amount of network bandwidth that's available to that instance is roughly half of that size. And this follows all the way down the line. So 4 of the C4 2X larges are roughly equal to 2 of the C4 4X larges, and so on and so forth. And the reason that things are set up this way is because of how we partition our instances. Typically, when you're running the largest instance, you're getting the whole physical server. When you're running smaller instances, you're actually getting a fraction of that server. Now, virtualization has historically gotten a pretty bad reputation because it's often used to manage the overutilization of resources. So you have more VMs than you have physical hardware to satisfy them. We, on the other hand, use virtualization for a lot of other reasons. One of the most important ones is for security and isolation from one virtual machine to another on the same piece of physical hardware. But we also use virtualization so that we can dedicate specific resources to specific customers. So taking virtual CPUs as an example. Again, with the exception of the T family, which is special for reasons we'll talk about later, when you're assigned a virtual CPU, you are the only customer that's using that CPU, and you're not sharing it with anyone else on the box. The same thing applies to memory and network allocation. We build EC2 instances with the goal of providing you with a consistent experience every time you use it, no matter what else is happening on that hardware. And the last thing that I want to talk about when it comes to choosing your instance, and I know it's pretty cheesy to quote your own EC2 documentation, but I really like the sentiment behind this. It's really easy to spin up an EC2 instance and install your application and do some testing in it. So instead of doing what I see customers do, which is launch a synthetic load testing tool to count the number of flops or IOPS or whatever they can get out of the instance, install your real application and test on that. So if you have a mobile app, simulate a real user navigating through it. If you have an HPC application, run some of your common models. If you have a business intelligence database, run some of your common queries. Use a real workload so that you know how your application is actually going to perform as you go into production. And not only that, you're going to be able to understand as you're testing different instance sizes how your application is going to scale and perform as you grow and scale out. Now I want to start digging a little bit deeper into the operating system and how the operating system interacts with the EC2 hardware. On any instance, physical or virtual, timekeeping is a really important operation. It's used for things like processing interrupts, getting the time and date, and measuring performance of cycles. most AMIs that you launch on AWS are going to use the Zen clock source by default. And the reason they do this is because the Zen clock source is compatible with every single instance that we have. However, it was around the time of the Sandy Bridge processor that the TSC clock source became available. Now, the TSC clock source, compared to the Zen clock source, is actually handled by bare metal and not the hypervisor. So every time you make a timekeeping call, you're going to be talking to the physical processor and not to a virtual device. And because of this, calls to this TSC clock source are going to be significantly quicker. So to demonstrate this, I wrote a very simple application. Don't worry about trying to read it. My code is terrible. I'm a sysadmin. But it does two things. It performs a large number of get time of day calls, and it also performs a little bit of floating point math. And here's the results of it with the Zen clock source. I also used strace to profile this application as it's running. And I really like strace because it'll tell you how many system calls are being made and the amount of time that they're taking up. So here you can see this test took about 12 seconds. And get time of day was the #1 call in that list. There were a lot of calls being made, and it took up a significant amount of time. The same exact system, the only thing I did is switch that clock source from Zen to TSC. The test now ran in 2 seconds as compared to 12 before. And if you look at that strace output, get time of day was so quick it doesn't even show up anymore. Now, I know this is a pretty simple application and a pretty extreme set of results, but I've seen some applications get as much as a 40% performance improvement just by switching their clock source from Zen to TSC. And I could tell that they would because I profiled them with strace, and I saw those number of timekeeping calls. So it's an easy change to make on Linux. You can see 3 commands here. The top command is going to list all the available clock sources on your system. So you can see if TSC is available, and if you're running a modern instance, it should be. The second command is going to list your current clock source. And if you launched a standard Linux AMI, that's probably going to be Zen. The last command is just going to hot switch your clock source from Zen to TSC. So if you're running a recently released EC2 instance, and you're running an application that's doing maybe some JVM debugging or performance tracing, or even SAP or database operations that have a lot of timekeeping calls, I highly recommend you switch to the TSC clock source because it could make a big boost in your performance. Another recent change that we made to the platform is giving you the ability to control the C and P states of your instances. So we launched this with the C4 8x large instance, but it's available on many more today. First, let's talk about the C state. So C states allow you to actually set the power savings features of that processor. So using a C4 8x large as an example, the C4 8x large instance has a base clock speed of 2.9 gigahertz. However, if you're only doing work on 1 or 2 cores, those cores can turbo boost up to about 3.5 gigahertz. But it does so by letting all those other cores on the system idle down. Now, this is really great when you are doing an application that requires a very high clock speed. But if you're doing work that requires all of your cores to be available and working, it can actually increase the latency of bringing up those idle cores. So I have some customers who will actually set this, the command that you see down at the bottom in grub, so it'll limit how far those other cores can idle down, so that when you go to use them, you won't have the increased latency of spinning them up. Next thing I want to talk about is the P states. P states allow you to set the desired frequency of your cores. So perhaps you have an application where you need consistency more than performance, and you want your cores to operate at the same clock speed all the time. Game servers are a pretty good example for these, which they operate in loops, and they expect that loop to take the exact same amount of time every time it runs. So customers with these needs will actually set the P state of their cores so that they don't turbo boost, and they just operate at that base clock rate all the time. Next, I finally want to talk about those T2 instances that I've been referring to and why they're special. So T2 instances, they're great general purpose instances. And they're actually the lowest cost instance that's available on EC2 today. So that T2 Nano, which is the smallest one, you can get for about half a penny per hour. And the T2 instances, they're great for workloads that have burstable CPU performance. These are things like database servers, websites, even, and especially development environments. With a T2 instance, you start with a baseline level of performance, and you're going to get that all the time on the instance. And as you can see, that baseline is different depending on which instance size that you go with. But the magic of T2 comes in with the burst credits that allow you to burst above that baseline. So we launched T2 instances because we saw that most customer workloads aren't using 100% of the CPU all the time. So using the CPU burst credits, it allows you to get the performance that you need when you need it and not pay for it when you don't. So let's dig into how those credits actually work and how you can use them. So you can think of the credits in a T2 instance kind of like a bucket. So you boot your instance, and you're going to get enough credits that are in that bucket to handle things like booting your operating system and launching your application and doing whatever work your instance was booted for. While your instance is running and doing all that work, you're going to slowly start pulling credits out of that bucket. One CPU credit allows you to burst for 100% of one core for 1 minute. Now, when the work dies down and your instance becomes idle, you're going to start earning new credits going into that bucket. Also, credits are going to expire out of that bucket if they're unused for 24 hours. So finding the right size of that T2 instance is important to make sure that you're always boosting. And to help you make sure of that, we offer 2 different CloudWatch metrics that you can monitor with your instances. So the first one in orange, this is your CPU credit usage. So this is going to tell you how many CPU credits per minute you're using as your CPU is spiking. The second one is the CPU credit balance. And this is going to be an important metric for you if you always want to be getting the burst performance out of your T2 instance. So if you always want to be in that burst level of performance and not at that baseline, you want to make sure that this credit balance never drops down to 0. If you're using something like auto-scaling, this is probably the metric that you want to start hooking on instead of CPU usage, because your CPU usage is going to drop once you exhaust all the credits in that bucket. The next instance that I want to talk about is the X1 instance. And the X1 is really exciting because it's the biggest instance that we have available on AWS. The X1, 32x large, it's a quad socket system, has almost 2 terabytes of RAM, and it has 128 virtual CPUs. So it's a massive machine that's really great if you have a big in-memory database, if you're doing some big data processing, or even some HPC workloads that need that much memory footprint all on a single machine. But when you have that much memory, effective management of it is even more important. On any system with multiple sockets, accessing the memory in the socket closest to you is always going to be faster than accessing memory in the socket in a remote socket. And this concept is called NUMA, or non-uniform memory access. Between those 2 sockets, you have what's called, especially on Intel systems, it's called a QPI, or a Quick Path Interconnect. And this is the bus that transfers memory from one socket to another. So let's look at the R3 8x large as an example. So this is a 2-socket box. And you can see that there's 122 gigabytes of RAM that are attached to each socket. Between each socket, you have 2 QPI links to transfer that memory from one socket to another. So if you have an application that's running in the socket on the left that's copying data from memory in the socket on the right, it's got to send that memory or send that data over those QPI paths, which, while fast, are never going to be as fast as accessing memory that's local to that socket. Now, when you go to the X1 instance, and you go to 4 sockets, things get a lot more complex. And NUMA is even more important. Compared to the R3 8X large instance, we now have far more memory per socket, 488 gigabytes of RAM on each socket. And you'll notice that instead of 2 QPI paths, because we have more sockets to spread them across, we now only have 1 QPI connecting each socket. So memory transfers from one NUMA zone to another are going to take longer on the X1 than they are on the R3. So what can you do about this? Well, if you've ever monitored a system, let's say with TOP or a process monitor, you'll notice that the process scheduler in your operating system is actually moving processes around from one core to another all the time. This scheduling helps ensure that your CPU performance is balanced over all the cores in your system. On Linux, it wasn't until around the 3.8 kernel that it started to take NUMA into consideration. So with that addition to the kernel, or with that addition to the scheduler, it's actually going to be moving processes closer to the memory that they're accessing, and also moving memory closer to the processes. The downside of this is that it can actually slow down performance of some applications, especially if they have a huge memory footprint. So if your memory footprint overlaps 2 different NUMA zones, if you're using a lot of memory for your application, it's going to be needlessly moving memory around from one zone to another, even though your processes are going to operate in both places and need access to them. So you can do a couple of things to mitigate this. On Linux, the first option is to set NUMA equals off in your grub boot parameter. And what this does is it actually disables all NUMA knowledge of that scheduler and of the system itself. So it sees one big NUMA zone overlapping all of the sockets on your system. So it's not trying to needlessly move memory around from one zone to another. The alternative is if you have an application that you can actually fit within a single NUMA zone, you may want to use an application like NUMA CTL when you launch whatever workload you have to lock your process into a single NUMA zone so that it'll only ever read and write memory that's local to it, and those processes won't be able to switch from one socket to another. Another thing to keep in mind when it comes to operating systems is how important the version of your operating system is. I was working with a customer not too long ago who was migrating a custom in-house developed application from on-premise to AWS. And they weren't seeing the performance that they were expecting to out of the system. Now, this was a pretty complex application, and testing it took a lot of work. So what we did is we found an analog, a performance testing analog tool online called eBusy, which exhibited the same exact behavior as they were seeing. So this is the first round of their tests. It was run on RHEL 6. And this is with eBusy. And we also profiled it with perf, which is another great tool to understand what's going on at a system level from your application. And here you can see the first time we ran it, we got about 12,000 records per second. But we noticed there was a lot of time being spent in system space in the kernel instead of user space. We also looked at the page faults and saw that there's about 1.5 million page faults just in this 10-second run. So obviously something is wrong. Here's the output of another tool that we used called flame graphs. Now, if you haven't used flame graphs before, I highly recommend it. This is a tool that was created by Brendan Gregg, who's given talks at reInvent before. And it's a really great way of understanding where the time is spent in your application and the code paths that are happening in there. So here you can see eBusy is the bottom bar in this chart. And the bulk of that time is actually spent in an madvise call, which is a memory management call. And that memory management call, it's going through a lot of different code, but eventually it ends up in a Zen hypercall, which accounts for all that system time that we're using. So we took this same exact code, and we recompiled it for RHEL 7, and ran it on the exact same type of instance. Just by recompiling it and moving it to the newest operating system, our performance went from 12,000 records per second to 425,000 records per second. And all that time that was spent in system space moved into user space where we'd expect it to be. We can also see that page faults went down from around 1.5 million to only 14,000. So what happened? What's the cause of this? Again, flame graphs tell the story. Here, this is the exact same flame graph generated from just a RHEL 7 system. Same exact code, same exact runtime. It turns out in RHEL 7, glibc changed the way that some memory calls happen. So instead of that long madvise call that ended up in that Zen hypercall, which ate all our CPU time, it's now doing an Intel optimized memory management task. So the moral of the story is that when you're moving to AWS, compile your application or run your application on the latest version of the operating system that it's compatible with. And if you can, recompile it, because it can make a huge difference. This customer, we even tried bringing over the RHEL 6 binary to RHEL 7 that was statically compiled, and we saw the same problems. Another subject related to memory, and this is going to be my last one on memory, is to disable transparent Hugepages. Now, Hugepages, it is a huge subject, so I'm not going to go into the depths of what Hugepages are, how they work. The link that you see at the bottom of this slide actually is probably the best article that I found that explains how they work. But transparent Hugepages are enabled by default on most Linux operating systems. Disabling transparent Hugepages and instead going to an explicit Hugepage model can significantly boost the performance of any application that's, of most applications, I should probably say, that are accessing a lot of memory. So I definitely recommend, if you're a memory-intensive workload, look at Hugepages, and especially explicit. Next, I want to talk about I/O. We have a few different instance families that are optimized for I/O usage. We have the I2 instance, which is an IOPS-based instance. It has a bunch of SSD drives. And then we have the D2 instance, which is dense storage and uses magnetic. But in order to get the best possible performance out of these instances, you need to be running a modern Linux kernel and on a modern operating system. And the reason for this is because of the split driver model that Zen uses to communicate. So let's say you're an application in the upper right that needs to write to a storage device. Inside of your application, or inside of your operating system, that application writes to a front-end driver. That front-end driver then goes through the hypervisor and talks to a back-end driver. That back-end driver then has to write to the real physical device driver before sending it down to the storage device. From there, data transfer happens through shared pages that need to be granted, that need permissions to be granted and released. And this granting process has a lot of overhead, especially on early kernels. Every time you need to talk to that disk, you need to talk to the VMM, get permission to write to the device, fill a buffer with the data you want to transfer, pass that data back to the back end, wait for it to be written, and then remove the grant. This is a really expensive operation that involves a lot of buffer flushing that only gets worse the more CPUs that you add to it. So to solve this, persistent grants were created. And with persistent grants, the permission to write to that device is actually reused for all the transactions between the front end and the back end driver. So grants don't need to be unmapped anymore, and that translation buffer never needs to be flushed. Because of this, you'll get significantly better performance for all your I/O operations, as long as you're running a kernel that supports persistent grants. So to validate that you are using persistent grants, or that they're enabled in your Linux kernel, you can simply just run the dmessage command and grep for the block front driver. Here you can see I'm running an I2 8x large instance. And as you can see, all of my volumes have persistent grants enabled. So if I haven't said it already, using a modern kernel is really important. I have a lot of customers that still use CentOS 6 because it's what they've been running in their data centers for years. But I've seen as much as a 60% performance improvement just by switching your operating system from something that's running a 2.8 kernel or a 2.6 kernel to a 3.10 kernel. The kernel that was released with CentOS 6 was released in 2009. And while it may not always feel like it, that was a really long time ago in the cloud computing world. So please use a modern operating system with a modern kernel. Now, along the lines of the split driver model, it was at the time of the C3 launch that we introduced a new way to talk to network devices, and that's enhanced networking. Now, under the hood, enhanced networking uses a technology called SRIOV, or Single Root I/O Virtualization. And what this does is it allows the physical network device to be exposed directly to your operating system so that your calls don't need to go through that hypervisor. Now, to use enhanced networking, it does have a few requirements. You do need a special driver to be installed in your operating system, and EC2 needs to be told to expose the network device in this different way. But as you can see, the network path is much, much simpler. Packets don't need to go through that hypervisor anymore, and because you're talking to bare metal, you're going to get a higher rate of packets per second and decreased jitter because the CPU is no longer involved in that process. It's free. Enhanced networking is free on all supported instances. And it's enabled by default in most AMIs. However, if you're doing an import of a virtual machine from on-premise to EC2, you probably don't have it enabled unless you've explicitly done so. I highly recommend it if you're doing anything that touches the network on an EC2 instance. And when it comes to network performance, we're still not done. Along with the X1 instance, we released the next generation of enhanced networking, which is called ENA, or the Elastic Network Adapter. Now, ENA launched with the X1, and it's beginning to roll out on newer and newer instances as we come about. So it's on the M416 and the P2 instance. But what ENA does is it now offers you 20 gigabits of network performance as compared to the 10 that you could just get with enhanced networking. It also has features like hardware checksums and receive-side steering to give you even more control of the packet processing pipeline so that you can make sure that you're getting the highest rate of packets per second. Now, when it comes to network performance, I want to touch briefly on the subject. And we have a deep dive at reInvent that I highly recommend that you go to on this. But when it comes to networking performance, that 20 gigabit and that 10 gigabit that you see listed on those instances, that only applies to instance communication when those instances are in a placement group. But if you do use placement groups, you can actually get bisectional bandwidth out of those instances. So that means you can get 20 gigabits out and 20 gigabits in at the same time. You'll also need to be using multiple TCP streams to achieve that. For things like talking to S3, any network traffic out of EC2 is going to be capped at about 5 gigabits per second. But it's easy to forget that networking throughput is also a function of instance sizes. I had a customer who was doing some performance testing with S3, and they weren't getting the performance that they were hoping for out of it. It turns out they were routing all of their internet traffic through a T2 micro NAT instance, which is definitely going to be your bottleneck. So definitely keep in mind the network performance of the instance that you launch. And if you care about it, use iPerf to test the throughput from one instance to another in that placement group. And just like network performance, EBS performance is also a factor of instance sizes. EBS optimization is a great way to get great EBS performance out of your EC2 instance. What it does is it creates a dedicated path for EBS traffic that's separate from your standard network traffic. It's actually enabled by default on a lot of our newest instances. So if you're doing anything that requires a lot of heavy storage utilization, make sure that you're using EBS optimized. Now, EBS optimized, we actually have the chart that you see here is just an excerpt from the EBS optimization pages. And this chart will show you that for every instance that supports EBS optimization, how much throughput you can get to EBS out of that instance. You can see how many IOPS you can get out of that instance. So it should definitely be your reference when you're using a workload that uses EBS heavily. So in conclusion, there are a lot of things that you can do to get great EC2 performance. At the bare minimum, use a modern operating system. Make sure you're using an HVM-based AMI so that you're talking to hardware as much as possible. Use enhanced networking. It's free, and it's going to significantly increase your packet performance. And always profile your application on your instances and test them to see how they'll perform. And when it comes to virtualization, I wanted to mention that our goal is to make virtualization as transparent as possible. Our goal, and eliminate any efficiencies that it can cause. Our goal is to give you bare metal-like performance out of your EC2 instance. And in a lot of ways, we're already there. So if you have any questions, we actually have a couple of microphones set up if you want to go up and ask. Otherwise, visit the EC2 documentation page and start testing your app. Thanks.